I want to pick up continuing to talk about the assumptions and things that we need to keep track of beyond the actual simple statistical calculation when we're looking at correlation and regression. So just as a quick reminder, regression and correlation assume that unless we tell it otherwise, the relationships it's looking for are linear, that the missing data is completely at random or at least is not directly related to a predictor with that we're actually measuring, and that the residual errors are randomly distributed. So when we're looking at homoscedasticity, we're also looking at homoscedasticity of the residuals, especially with a continuous variable. So the residuals are the difference between the actual value of y and the predicted value of y. So the distance from the prediction line to each data point, the greater the total of the residuals, the worse the fit of your model. So when we're looking at the residuals, we're actually talking about not the initial statistical analysis of two variables in one sample, but when we start actually using that information to make predictions in future samples. So we're measuring x1, for instance, but we're not measuring x2, we're predicting x2. But down the road in time, we then actually get x2. So for example, we might be measuring a performance test that we use to decide if we're going to hire someone. And the reason we're using this performance test is we actually correlated that performance test with actual performance of employees and found a strong relationship. So now we're going to use that performance test in new applicants. Those that score high in the test are the ones that we hire. But once we hire them, we're actually going to get the data of their performance, and then we can look at the residuals. How was our prediction versus how well they actually performed? And again, the worse the fit, the smaller the R of the first model, most likely the greater the residuals, the bigger the difference. But just as we're looking for homoscedasticity, so a sameness in how the variance is between two variables in an initial sample, we also want to look for homoscedasticity in the residuals. In other words, we might have a situation where we do find that it is predicting, but it predicts very well at low levels and not as well at high levels. We're going to get heteroscedasticity, not just in the initial relationship, but we might actually find that we do not have an issue or a violation of homoscedasticity in the original sample. So the actual study we did, where we basically used existing employees, gave them the performance test, measured their performance, which we already had on file, and found a nice linear relationship that was homoscedastic. There was no issues or no differences in the variance of our prediction in that initial sample from group one versus, or basically from measurement one to measurement two, the prediction test versus the actual performance. But we also want to look for homoscedasticity if we later check the residuals of error once we start using that tool. Because what might actually happen is that though there was no problem with it in the original model, we might find that in reality we start seeing something different. We see that shotgun pattern. And what this would represent is that at low levels of performance and low levels of performance measurement, so basically the predictor, there's a pretty strong relationship. But as we get to high levels of performance and high levels of predicted performance, we find the prediction is not as good. There's a lot more variance, there's a lot more error. And that's going to be a problem because we're assuming that the amount of error in our prediction should be about the same high to high, medium to medium, low to low on those two variables. So we're going to continue reviewing correlation and simple regression. So again, correlation. We're going to talk a little bit about some of the formulas for Pearson correlations, and we're actually going to get into how you actually calculate whether a Pearson's correlation is significant or not. And it actually is a separate test that is being done. And that separate test is especially important as we move to basic regression, and we're going to be talking about the interpretation of coefficients. And again, just a quick reminder that actually from last semester, it was actually Francis Edgeworth that actually originally wrote the correlation coefficient equation. He just doesn't get credit for it because he published it in a small unknown journal, and he wasn't British like all the other statisticians. So it teaches you that it's not a good idea to be Irish and an initial founder of a statistical technique. You don't get it named after you. So correlation. Again, examines the relationship between two continuous variables. Pearson's product moment coefficient correlation is the full name that we use when we're doing a correlation between two continuous variables. Spearman's correlation is what we're going to use if we're using ordinal data or if those continuous variables are just pesky and they can't be determined to be parametric. So for example, if you have a continuous variable that is skewed, and you've tried transformations, you don't think it's appropriate to remove outliers, the reality is it's skewed data. At that point, one of the solutions is you change that data from continuous to a ordinal data, so first, second, third, fourth, fifth, etc. And then you run it through a Spearman's correlation. And the reason for this is Spearman's correlation does not have those assumptions of normalcy of data. We also have the point biserial correlation, and it is used when one variable is continuous and the other is dichotomous. Now, a quick note, as far as statistical techniques, the Spearman correlation is different than the Pearson product moment coefficient correlation. However, a point biserial correlation is the same, technically, the same equation is being used as the Pearson product moment coefficient. It's simply we're naming it something else to let people know that it's not two continuous variables. It's a continuous variable and a dichotomous variable. Once again, a quick reminder, the strength is simply the value of R from 0 to 1.0, and the larger that number, either positive or negative, the stronger the relationship. The direction is the trend of the relationship. If the number is positive, as one variable increased, so did the other. If the number is negative, then as one variable increased, the other one decreased. And again, it assumes a linear relationship. And one of the first things that we're going to do when we run a correlation is we are going to just visually look at the scatter plot. So beyond the actual statistics, because all the statistics are telling us is what is the estimated line of best fit, how much of an angle that line of best fit has, and that's referred to as R. So a perfect one-to-one relationship is going to be an R of 1.0. An R of 0 is going to be a flat relationship. And finally, it's going to tell us whether that pattern is statistically significant or not. But we also want to look at what's actually happening in our data. So beyond this line of best fit, which is what we're going to get from the statistical analysis, that scatter plot is going to give us a good visual representation of just how good of a predictor is this. And you'll notice that in general, this is better than nothing, but it's certainly not very accurate. If you have an SAT of 1200, you might have a GPA as low as 2.0 and as high as about 3.4, it looks like. Likewise, if your SAT was 1000, you could be between a 2.5 and a 3. And most people tend to fall in this middle range of there. And again, so their SAT was somewhere between 1000 and 1200, and their GPA somewhere between 2.0 and 3.5. But the line of best fit would basically indicate that if you had an SAT of 1100, your GPA prediction would be 2.7. And notice no one actually is on that line. All of the GPAs at 1100 SAT are actually above the prediction. That doesn't mean the prediction is useless. It means that the prediction is not completely accurate. It's giving us a good guess. It possibly is even statistically significant, but that scatter plot gives us an idea of what's actually going on and how much we can rely on these predictions. So again, each individual person is represented by their score on both variables. If they're on the line, that's accurate prediction. If they're off, the difference between the line prediction and their actual score is the residual of error. So how much error was there in our prediction? So in this case, this particular person, we predicted them to be at 2.5. They were actually at 3. The residual is 0.5 GPA. The stronger the correlation, so the bigger the R, not only are we going to see more angle in the prediction, we're also going to see a tighter grouping. So it basically represents two things. How much variance is there? The larger the number, the less variance, and the less residuals in error of prediction. And also the stronger the relationship, the more angled the line is going to be. And again, if it's a negative relationship, as one goes up, the other one goes down. But again, in this case, it's a weaker relationship, and we see a lot more residuals, a lot more error. That doesn't mean that an R of negative 0.2 is a bad R that we shouldn't use. It simply tells us that we could trust it less than, for example, an R of 0.8, which is going to be a more accurate prediction. And again, if there's no relationship, that line of best fit is going to be flat. It's not going to be angled to the positive or the negative, representing there really is no relationship. Now remember, and we'll hit this again later in the lecture, we do need to be a little cautious here because these are all based on the assumption of linear data. if you do not have linear data, there may be a very strong pattern represented between your two continuous variables that is basically just not being picked up by a test that's looking for a linear relationship. And that's one of the other reasons we always want to spend at least a few seconds taking a look at that scatter plot, because that scatter plot can sometimes indicate a problem we might have with our actual assumptions. So again, if we read the strength of the relationship, the degree to which the points in the scatter plot cluster around that imaginary line of best fit represents the slope. The stronger relationships, the oval is elongated and thin. All the data points are going to be fairly close to that line of prediction. And as the relationship gets weaker, we're going to start to see a weaker and weaker relationship as far as the dots or the predictions are going to be farther and farther away from that line of best fit. So the numerical representation of the correlation coefficient. Correlations are indicated by R lowercase, and they range from -1 all the way to +1. Again, the sign is simply an indication of direction. And the effect size is simply squaring the correlation coefficient, so R squared. And that's the proportion of variability in our predicted that you can be accounted for by our prediction. In other words, we have a predictor and we have an outcome. The predictor is X, the outcome is Y. So R squared gets rid of the negative sign. So it'll always be between 0 and 1.0, and 1.0 would be a perfect correlation 100%. Generally, R squared will always be lower than R, except in that case where R is 1.0 or -1.0, and then R will be 1.0 or, well, only 1.0. And generally speaking, we often convert R squared to a percentage. So if we have an R of 0.21, that would be 21% of variance is accounted for by knowing our predictor. So knowing X gives us 21% of variance explained in our outcome. We can also represent this with Venn diagrams. So if there's absolutely no relationship, X, our predictor, and Y, our outcome, there's no overlap, there's no prediction. The common variance, the R squared, is the amount of overlap. The stronger that overlap, the more variance explained. So in the middle here, we have a predictor X that's explaining about half of the prediction of Y. And as we move forward, we get a stronger relationship off to the right, where at this point our R squared is 0.96. So our predictor is explaining 96% of the variance in Y. There's very little left that's not being predicted. That would be an awesome relationship. Now, generally speaking, when we look at single correlations, we rarely are going to find that strong relationships. We're just looking to explain anything in our actual outcome. And that's one of the reasons we often will use multiple regression, allowing us to use multiple predictors to explain more of Y than any one predictor would allow us to. So again, conceptually, our Pearson's correlation, the top of the equation, like with all equations, is simply the degree to which Y and X vary together. It's our effect. And the bottom of the equation is everything left over, everything that's not effect, the degree to which X and Y vary separately. Mathematically, it's a little more complex, and this is one of the equations we can use, but what we were mainly looking at as far as hand calculations was sum of products divided by the square root of sum of squares X and sum of squares Y. So the sum of products is actually a mathematical equation predicting how much of covariance there is, and the sum of squares for each of the variables is how much of just total variance there is to begin with. And again, the sum of products is simply each person's individual score of X minus the mean of X multiplied by each person's individual score of Y minus the mean of Y and added together. So if we had 10 people, we'd do this 10 times. 10 people's scores on X minus the mean of X multiplied by Y minus the mean of Y. Sum all those together, and that's what goes on the top of the equation, sum of products. The sum of X is simply the score of each person's X minus the mean squared to make that a positive number. And again, we add it up. We do the same for Y. We multiply those two numbers together, and we take the square root, at which point we simply divide. And that gives us our R. And in the case of Pearson correlation, if all we're doing is a simple correlation, we can then go to a frequency chart to find out, did that R exceed the minimum needed for us to be able to claim significance of P of 0.05?